Okay, so now I'm going to show you how to do quintic polynomial for or joint space control for the UR5, and then we'll go to the Cartesian space. Here is, we'll go pretty fast, but then I'll explain the code. So it starts with that, and then it just does really large joint angles through time. Okay, so it ends there, and I specify the initial pose and the final pose. So let's look at the code. Since the joint velocities, joint angles, which is clearly smooth. Okay, there's a lot of stuff here which we don't want. We just need to get to the meat of it, which is essentially specifying the initial position, so Q0, the final position QF. Okay. I use a quintic interpolation. So this function I wrote from scratch, quintic interpolation. Here what I do is I use the equations which I derived from the earlier part where you remember there were symbolic equations. I just put them there. Again, it's not the best way to do it. You should probably take the A matrix and then invert it numerically, but I chose to use the inverted A matrix here. So then I get Q, Q dot, and Q double dot, and I pass this back. So here we have Q and U, and then I specify Q in Q pose and U to Q well. This is basically the position velocity. I'm still doing MJ forwards. There's no dynamics involved here. And then this is actually kind of slow because I'm using time step. The time step, I think, is 0.002. So if I want it to be fast, let's just do 0.1. And then I just save the Q and the U. And then I plot the Q and U. So let's put a bigger timer here. So let's say 20. Okay, now it'll go much faster than before. And then it does a plot. So these are joint velocities. You can see it starts and ends with zero velocity. These are for the 6 joints, 0 to 5. And then angles 0 to 5. You can see it starts with whatever Q0 was and whatever QF was, and the slopes are 0, which means the velocity is 0. So this is just going from point A to point B. The best way to do it is to quintic. Now,